Hello YouTube. I wanted to do a quick video talking about misrepresentations of the standard model of the shape of the Earth. That is the model that states that the Earth is almost a perfect sphere, but not a perfect sphere. An oblate spheroid and an irregular oblate spheroid at that. And this model, the standard model, if you like, of the shape of the Earth is often misrepresented quite badly by, particularly by people who still believe that the Earth is flat in spite of all the evidence to the contrary. But it's also misrepresented sometimes to some extent by science and by people who understand that the Earth is in fact roughly spherical, but they misrepresent it in a different way. So there are two levels of misrepresentation. The flat earthers completely misrepresent the model, almost always, in order to try to make evidence fit with their misconceived idea that the Earth is in fact flat. And what happens in other cases is that the shape of the Earth is approximated. So it's approximated to a sphere or approximated to an ellipsoid, in order to provide either useful tools or to have a simplified understanding of what the shape actually is and where we are on the Earth's surface. So the particular video in question was this one, and I'll just like to play a little bit of it and explain how utterly misrepresented the this Earth model, spheroid Earth model, is.
There we go. There's a picture of it. And I think I've got the maths as well. Let's just dig that out. Give me a second.
Are there any fantasists out there that can come up with nonsense evidence to support the shape of the Earth?
Here we go. So, sorry to interrupt. Can I just show this to the audience? So, this is what you were talking about. I don't know if you can see my screen. The flattening factor F for the WGS 1984. Yeah, so the flattening factor equals A, the equatorial radius, minus C, polar radius, derived, okay, that's this, divided by A, which is the same figure again, A. So this figure here, very similar, slightly smaller when it comes to the polar radius, the derived figure. But the end figure, 1/300. You end up with a disk that is 33 miles in kilometre, and it's an AE projection. This is the world of the WGS84.
So Nathan Oakley misspoke a little bit there when he said a disk of 33 kilometers. I think he meant 33. I don't know exactly what he meant. But what he was saying is that the WGS84 is in fact a disk only 33 kilometers thick, is what I believe he said. Hopefully he didn't mean it's 33 kilometers across from side to side, because, well, that would just be ridiculously small. But this is a complete misunderstanding of what these values and units and formula actually are, and a complete misrepresentation of what WGS84 actually is. And to misrepresent it in this way either displays extraordinary stupidity, to the point that I'm pretty sure I could explain this to a 13-year-old child, and they would get it straight away. And possibly even a younger child would get it straight away. And yet Nathan either just is extraordinarily stupid in his misunderstanding and misinterpreting of this, or his willful misinterpretation, deliberately done to try to provoke people to join the debate, or to claim something that is false for whatever reason. So let's have a look at what this WGS84 actually is. I mean, the information is here on the screen for you. It has an equatorial radius of 6,378 kilometers. It has a polar radius of 6,356 kilometers. So that's enough. Okay, that tells you any shape that has those two radii. The fact that it's got two different radii means it must be an ellipsoid, and it's an ellipsoid that is very, very nearly spherical and is a radius of 6,356 to 6,378 kilometers. It's a pretty big object. Anybody who understands anything at all about mathematics knows that this F factor is simply describing what the relationship is between, or a relationship between, the two radii. It's not telling you to squash the whole thing 300 times or anything of that sort. It is simply describing the relationship. So you take the larger one, subtract the smaller one, and you're left with a number, which in this case is going to be roughly 21.6, so 21.5 and bits. And you divide by the length of the other. And that fraction tells you something about the relationship between those two lengths. That's all that is doing. It is not a function that you apply to the ellipsoid to get its real shape or anything of that sort. So that's obvious. That's there on screen, and any fool and anybody with rudimentary understanding of basic functions in mathematics, all you need to be able to do to understand this is understand subtraction, division, parentheses, and what an equal sign means. So that's obvious, and it's clear that Nathan is completely and grossly misrepresenting part of the spheroid Earth model, the WGS84 coordinate system or datum system. Now, it is true that all or many things misrepresent what we know to be reality from measurements. So curvature calculators misrepresent the shape of the Earth in another way. This one, the Metabunk one, explains the radius that is used for calculations, and it uses a single radius to generate a three-dimensional object, or in fact in its calculations here it probably just generates a circle and makes its calculation based on that circle. This is a sort of diagram explaining the diagrammatically what is being calculated. So it uses a radius which is 6,371, which is neither the equatorial radius of the Earth nor the polar radius of the Earth, but somewhere in between. It's a very good approximation. The Earth is very nearly a perfect sphere. And if you want to know the relationship between 2 points on that surface and how much should be hidden from a particular viewing height, then you can get a very a good idea of what should be observed by simply using a circle and making this kind of calculation. But it's not accurate to a high degree. It is not going to tell you exactly what should be seen or not seen. Now, lots of people, myself included, use it to show that particular observations are within the sort of error, if you like, that's built into this approximation. That what is predicted by Metabunk calculator matches fairly well what we observe in reality, and that's fine as long as you understand that all you're doing is trying to do something that is an approximation, that it gets close to matching reality without necessarily matching reality perfectly. And the amount of the error will be affected by many different things. And there's been lots of debates about refraction. They try to, on this particular calculator, factor in some refraction element. Other calculators do more. They have a sort of zero standard and a non-standard refraction factored in. But these, again, are estimates. They are not designed to give you a perfect answer to the question. They're simply there to give an approximation. And so, yes, it's a misrepresentation of the true model, but it is a useful misrepresentation in that it is only slightly inaccurate, and it is known to be slightly inaccurate, and that's fine. So let's have a quick look at the WGS84 and what it kind of is. And I don't want to spend too much time on this because it is complicated. But I did a quick Google search, and one of the documents that I found was this Ordnance Survey Great Britain PDF document. And if we I really recommend having a read of this, because it really will explain a lot about how mapping is done, how coordinate systems work, how the Earth is shaped, and how we know that it's shaped that way. And it gives a good start point anyway to lead on to other things. It will take some effort though, guys, especially if you're a little bit challenged in that department, as some people seem to be. Let's go to this section 2, the shape of the Earth, and just read the very first sentence. When you look at all the topographic and oceanographic details, the Earth is a very irregular and complex shape. Now, immediately, I'm thinking of something that is incredibly lumpy and bumpy and not something like a sort of random rock shape or potato shape or something like that. But let's read on. If you want to map the positions of those details, you need a simpler model of the basic shape of the Earth, sometimes called the figure of the Earth, on which a coordinate system can be based. And then the details of the irregularities, if you like, can be added by determining their coordinates relative to the simple shape to build up a full picture. Okay, so that's what is done in geodesy and geodetic surveying. What they're trying to do is to take, let's take a simpler model of a basic shape, and then let's fit or see how the actual measurements and the actual data fits onto that model, that simpler model. 2.2. the Earth is very nearly spherical. Okay, now where does that come from, that statement? Well, that statement comes from millions, probably billions of data points, of actual data measurements of the Earth, originally from surveying on land and more recently from satellite observations from space as well. And at this point, the debate over whether the Earth is flat or not should be over. Every measurement made leads people who have looked at those measurements to this conclusion that the Earth is very nearly spherical. However, it has a tiny bulge, equatorial bulge, making the radius at the equator about 1/3 of 1% bigger than the radius at the poles. Now, this sentence is crucial to what Nathan Oakley did. Okay, the radius at the equator is about 1/3 of 1% bigger than the radius at the poles. About 1/3 of 1% is 1/300. (1/300). The difference between the radius at the equator and the radius at the poles is different by this much. This is not some magic Earth squashing to a flat plane factor. And the article goes on this is to say that the simple geometric shape which most closely approximates the shape of the Earth is a biaxial ellipsoid. That simply means an ellipsoid with two axes, and you generate that shape by rotating a simple two-dimensional ellipse around its shorter axis, and you get something which is very closely approximating to the shape of the Earth, but not the shape of the Earth. This is because the ellipsoid shape doesn't fit the Earth perfectly. And then it goes on, there are lots of different ellipsoids in use and so on, and explains a lot about how that actually works. Now, we also have in here quite a lot of reference to WGS84. And if we go to this particular section, we get some information about WGS84. The datum used for GPS positioning is called WGS84. So it's a datum. It's effectively an ellipsoid, if you like, that is centered upon the center of mass of the Earth. Consists of a three-dimensional Cartesian coordinate system and an associated ellipsoid, so that WGS84 positions can be described as either XYZ Cartesian coordinates or latitude and longitude and ellipsoidal height coordinates. The origin of the datum is the geocenter, the center of mass of the Earth, and is designed for positioning anywhere on Earth. So, to suggest that the WGS84 is in fact a flat disk of any sort is incorrect. It's a coordinate system and an associated ellipsoid. And that ellipsoid has the coordinates that the dimensions that were given earlier. Essentially 6,356 or 6,378 kilometer radius. To suggest anything different is just absurd. Now, this whole article goes on to explain how different ellipsoids are used and how the real shape of the Earth is in fact a geoid, a complex shape. There are things called terrestrial reference frames and so on. I'll go back up here. There's a diagram that's quite useful to explain, as long as people don't misunderstand it. This is a very exaggerated diagram. So the grey area is a cross section through the Earth, and it shows how irregular the Earth is. Now, this is grossly exaggerated. If this were done to scale, you would not be able to see any of these irregularities. They would be smaller than a pixel. But it's done here to illustrate the point. There's a globally best fitting ellipsoid which is given in black, which is the best fit you can get, taking all points around the edge of the Earth into account. And it fits very, very well here in this particular location, and here in this location, and down here in this location, but does not fit well here, or here, or here, or here. And you can use other ellipsoids that fit those regions better. Remember, what they're fitting to is the actual measurements made of the surface of the Earth. It's not, we're not building a shape and then trying to distort the actual measurements to fit onto it. It's the other way round. The measurements actually define the shape and the reference data criteria that we use, or that are used. I shouldn't say we. So this kind of gives you an idea of the irregularity of the Earth, how an ellipsoid doesn't quite match it perfectly, and how we end up with different ellipsoid being used for different locations because they fit better with the actual data, and the whole thing fits together into a pattern and a model. Now, that model, the standard model of the shape of the Earth, is not finalized. The Earth is, broadly speaking, spherical. It's not a perfect sphere. It's a bit squashed. It's a bit ellipsoidal. It's also irregular to a local level to small extent as well. So it doesn't even fit the ellipsoid shape perfectly. It's a bit lumpy and bumpy. And that's why when you use curvature calculators and try to match them to observations that are made on the Earth, they will match closely, but not always perfectly. And of course, refraction contributes as well. Does this mean that curvature calculators are useless? Of course it doesn't. And over long distances, particularly, and over large numbers of uses, we find that the curvature calculators are always close to the observed values. And because of that, this is further confirmation that what is observed in nature pretty much matches a sphere with a radius of 6371 kilometers, but not perfectly. And so we know it's going to be roughly spherical, but not exactly spherical. What these observations also confirm is that it is most definitely not flat. It is not a flat plane, and at no no data gathered that in any quantity confirms it's a flat plane. So that's really all I wanted to say. There's plenty of stuff out there. You can get images and loads of information just by typing in WGS84, and you'll get all kinds of articles that explain how the system works, what it is, and so on. Please go read some stuff. And Nathan, please you go and read some stuff, and get Anthony and get Chris to read some stuff as well, so that you do not continue to misrepresent what things like WGS84 are and things like the shape of the Earth are. Thank you for listening, and see you again shortly with another video. This one will probably be about Moorgold Lighthouse on the Isle of Man.